Hi there, and welcome to Mr. Morgan's Math Help for Algebra 1. We're still looking at Unit 1 on sequences, and today's lesson is lesson number 7 on what comes next and what comes later. All right, so again, as always, this is the part where we're going to talk about make sure you do your homework first and then come back here to check your work, not just look for the answers so you don't have to do the thinking. The thinking is what's going to help make you a better mathematician, a better learner, and just a better student overall. And today is the magical lesson number 7 where they did say it all starts coming together by this point, so let's see if that's true. Here we go. All right, for the first one, it says find the common ratio for each of the geometric sequences. Now, so we talked before about a ratio always goes with a geometric sequence, and usually that means that we're going to be multiplying, things together. There's going to be something happening there, not adding. The adding goes together with the arithmetic sequences, which are going to be more of the differences. Okay, so all right, so we're looking for how we go from one number to the next. So to go from 2 to 4 is multiplying by 2, 4 to 8 is times 2. So my common ratio here is going to be 2. Again, the answer is 2, but we can think about this being as multiplying by 2. For number 2, 5 to 15 is going to be multiplying by 3. The next one, negative 5 to 10. Well, 5 to 10 is times 2, but we see that it's going from negative to a positive. So if I multiply by a negative 2, negative times a negative becomes a positive. And the next one, if I did 10 times negative 2, that becomes a negative 20. So indeed, we would say multiplying by a negative 2. And the last one's a great one here. We're going from 40 to 10, so you can think about 40 times what number is going to get you to 10. Well, to solve for x, we divide both sides by 40. And that gets reduced down to x equals 10 over 40. This reduces to 1/4. So in this case here, our common ratio is 1/4. Okay, so that's our ratios for those geometric sequences there. All right, now that's the ready part. Let's get set to go. It says fill in the blanks for each table and identify the type of sequence. The type of sequence, right? That means whether it's going to be arithmetic or geometric. Okay? Then write the recursive and explicit equation for each sequence. Okay, so here we go. So for the first one, we're going from 15 to 18. Looks like we're adding 3. Checking one more, we go 18 to 21. We're still adding 3. So because we're adding 3, this would be an arithmetic sequence. All right, let's continue to fill in the table though. 21 plus 3 is 24, and 24 plus 3 is 27. Now in terms of recursive is the which one comes, just before it, or which one comes next, sorry. F of n is going to equal the previous term in minus 1. And in this case here, we're adding 3. Okay, so we're adding 3 to that one right there. Now, the easiest way to find our explicit, our f of n, is going to be to say that I know that I'm adding 3, and so because I'm adding 3, I'll do 3 times n, whatever the number is, and then I'm going to go back one space this way. I'm going to subtract 3 to see where am I at 0. At 0, I'm at 12, so we would say add 12. 3n plus 12 becomes my explicit equation there. All right, number 6. Okay, so here we have going from negative 2 to negative 6. That looks like I am subtracting 4. Okay, it could also be that I'm multiplying by 3. So let's take a look at the next one. Negative 6 to negative 10. Yep, still going down 4 more there, aren't I? So definitely not multiplying there. So because I'm subtracting, I have a common difference there. This is arithmetic there, right? And it's going to be minus 4 is what's happening. So for my recursive statement, I would say that the function of n is equal to the function of the previous term, n minus 1 minus 4. For my explicit, let's finish this up real quick here. I am going to have minus 4 more, minus 14, and minus 18. I would say the function's going to be equal to whatever I'm doing right here. So minus 4n. And then we're going to go back to our 0 value real quick. So I'm going to add 4. So 4 minus 2 is a positive 2. So we're going to say negative 4n plus 2 for explicit. Number 7. All right, going from 3 to 9, I could say it's plus 6, or I could say it's times 3. So 9 to 27, it's not plus 6, definitely times 3. So let's go with times 3. So because I'm multiplying by 3, this is going to be a geometric sequence there, which means my recursive function of n equals the previous term times 3. All right. Now, we talked before when we have geometric here, we can expect to see some sort of exponent in our explicit equation down there. Okay? So if you think about this one, what's happening from one to the next? Well, here we have 3, and here we have 3 times 3. Here we have 3 times 3 times 3, okay? And that's going to continue there. You can have some other values you need to fill in there for 3 times 3 times 3 times 3, and so on. So what we have essentially is we have 3 to the n power, where n is 1, and then we have 3 to the second power there, so that's 1, 2. So our explicit statement is simply going to be the function is equal to 3 to the n power. Make sure you complete this and figure out what those last two terms are going to be. Number 8. All right, 48 to 12. And then 12 to 3. Definitely not just subtracting something, because this is going to be 9. So it's not going to be subtraction. It looks like we're multiplying by some sort of fraction. Some sort of fraction to get us from 48 to 12 or 12 to 3. Now 12 to 3, I recognize that that is, in a sense, oops, change my line there. Because I know 12 to 3, 12 divided by 4 equals 3. So because I can say, well, it's divided by 4 is the same as what? Multiplying by the reciprocal, or multiplying by 1/4. So we know we're multiplying by 1/4, which means that this is a geometric sequence. Multiplying by 1/4. All right, so no problem there. So for the recursive, we would say that f of the previous term, n minus 1, f of n equals the previous term times 1/4. Okay, so we're good there. So let's take a look here what this could look like then if we were to then draw our lines to say, well, what's happening for each one? Well, here I have 48, and here I have 48 times 1/4, and then I have 48 times 1/4 times another 1/4, and that's going to go on and on and on. So what's taking place here? Well, essentially, I have my 48th times a fourth, but the number of fourths that I do depends upon the term that I'm at. This one has no 1/4, right? So I want a 0 there. So, I want a 1 there. So the best way to do that is I want this to work there. So if I do n minus 1, then my first term becomes simply 48 times 1, right? And then the other ones all work out just fine. So for our function, we would say function of n is equal to 48 times 1/4 to the n minus 1 power. All right, number 9. It says add 2 more points in the graph that will fit the sequence, identify the type of sequence, and then write the recursive and explicit equation for each one of the sequences. Okay, so we can see here that we are going down 2 and over 1, down 2 over 1. So we'll continue and go down 2 over 1 and put a point there, and go down 2 over 1 and put a point there. So those are my points there. Because I can see that essentially what's happening is I'm just going, I'm subtracting 2 essentially, right? If we make a little chart here for ourselves, we make an x and a y. Well, let's keep it in terms of what we've been doing. We've been doing n and f of n. Okay, when we have 1, 1, 2, 3, 4. When we have 1, we have 9. When we had 2, we had 7. When we had 3, we had 5. 4 is at 3, and 5 is at 1. So we can see here that we're just simply subtracting 2 each time. Because we're subtracting 2 each time, we would say this is an arithmetic sequence like such. In terms of a recursive formula, the function of n is going to be the previous term, n minus 1, and then we're going to subtract 2. For our explicits, what we want to do is we want to say we're going to take what's happening here, our change, minus 2n, and then we also want to see then, well, where does it cross the y-axis at? So I want to go back a term. So I think about going back a term, I'm going to go this direction and this way to get a 0. So instead of minus 2, we're going to add 2. So 9 plus 2 is 11. So we would say we're going to add 11. So that becomes our explicit. And if I was to mark it out here on my board, I would go 1, 1, 2, and my point would be right there at 11. And so that's where this term comes from. So that value is right there. Or we can also see it coming from here. Okay. Next one. Add 2 more terms. Well, we can see we're starting here. Here's 1 and here's 2. So at 1, we're at about a half, 0.5. However you want to think about that, 0.5, half, right? At 2, we can see we're at 1. At 3, we're at 2, and so on, okay? So there's my n, my f of n. So moving from here to here, I'm multiplying by 2, multiplying by 2. So to make the next 2 steps, or 2 points, I multiply by 2 again. 2 times 2 is 4, and then 4 times 2 is 8. And then we can plot those out. 4 is 4, and 5 is at 6, 7, 8 right there. So it's become my points there. In this case, this is going to be a geometric equation, right? Because we're using multiplication right there, which makes my recursive, the function of n is equal to the previous term, and then whatever I'm doing, times 2. For the explicit, the function of n is going to be equal to, well, in this case here, I want to look at what I'm doing. I have 0.5. Next one I have 0.5 times 2. Then I have 0.5 times 2 times 2. And then 0.5 times 2 times 2 times 2, and so on. Okay? So I know I'm going to be multiplying by 0.5. That's okay there. And then I'm going to be multiplying by 2. But how many 2's? In the first case here, I don't want any 2's in this first line right there. I want it to be equal to 1. So that means if my n is 1, I don't want to just say 1 because that's going to leave it as 2. I'm going to do n minus 1, so I end up with 2 to the 0 power, or ends up becoming 1. So that becomes my term for right there. You could also write this as a fraction if you wanted to. If you saw that as the 0.5 could be, instead of a 0.5, you could call it a half. You could say this is equal to 1/2 times 2 to the n minus 1, because 1/2 times 2 does get you there. So instead of a decimal, instead of 0.5, that becomes 5/10, which is a half. So you could use a half here if you chose to. All right, and finally the go section. Write the recursive and explicit functions for each of the arithmetic, I've been spelling it wrong all the time, sequence for problems 11 to 15, then graph it, and then label it. Spelling is not my strong suit. Arithmetic. All right, so they're arithmetic, so that means we're going to be just adding things, right? Not geometric, just adding. So 2 to 4 is plus 2, 4 to 6 is plus 2. So we know we're just adding 2 there. So the function of n is going to be equal to the previous term, n minus 1, plus 2. Okay? In terms of the explicit, what we would look at is we would say, well, we know the function of n is equal to 2 times n, and we don't know if there's something else that goes there. So let's just make a little chart real quick. N f of n and put some points down. We have 1, 2, 3, 2, 4, 6, and then we also had 8 as well. So we know we're adding 2. So if I back up 1 and subtract 2 to find the 0 term, I'm actually at 0. So we just leave it as 2n right there. You don't need to say plus 0. For graphing it, we can draw our graph. We can draw a graph. And we have 1, 2, 3, 4. And then 1, 2, 3, 4, 5 is here. 6, 7, 8, 9, 10 is here. So at 1, we are at 2. At 2, we are at 4. At 3, we are at 6. And at 4, we are at 8. And now we have graphed it, and it looks great. Let's label this here. This is our n. This is our f of n, and we're set. Okay, number 12. All right, we can see we are doing what? We are adding 3, adding 3. So recursive is going to be f of n equals the previous term plus 3. To find out the explicit, we know it's going to be f of n equals 3 times n, because we have a 3 there. But I want to see what comes after that. So if I subtract 3, I'm at 0, 0, so we leave it just like that. So graphing this here, okay, I'm going to say this is 1, 2, 3, 4. And we can see at 1, we're going to go up 1, 2, 3. And then we're going to go 4, 5, 6 for 2, 7, 8, 9 for 3, 10, 11, 12 for 4. And this becomes our n and our f of n, and that's our graph for that one there. All right, moving on to number 13. It says that Claire has $300 in the account. She's going to take out $25 each month is what she plans on doing there. Okay, so what she plans on doing here, recursive, we know that it is going to be f of n equals f of n minus 1 minus $25. Okay, so for the explicit though, this one's a little different here. We know it's f of n, and that's going to be, we know we're taking out $25 times n, but our starting point is actually going to be, we know what that's going to be. She starts at $300. So that's where she has at the 0 point there. So our 0 point here, if we draw it like so, we could go 1, 2, 3, 4, and this becomes 100. 1, 2, 3, 4, 200, and 1, 2, 3, 4, 300. So we know at 0 we're there, and every month she takes out $25. So we have 1, 2, 3, and so on. And it would go just like that to continue out for the rest of the year. All right, each day Tanya decides to do something nice for 2 strangers. What's the relationship between the total number? She helps out each day. So every day she's doing something nice for 2 people, right? So every day we're doing 2 more people. So we would say the recursive would be the function of n minus 1 plus 2. In terms of the explicit, we would say that basically it's 2 times n. And we know that on day 0, she did nothing, right? So on the first day, she hadn't talked to anybody, but day 1 was 2 people, day 2 was 4 people, day 3 was 6 people, and so on. So we could graph that out like so. And we have 1, 2, 3, and we have 0 on day 1, and day 1, or 0 on day 0. 1 was there, 2 is there, and 3 is there. That becomes your f of n, that becomes your n, and you're set. All right, one last one. We can see here we have 6, we have 12, and then we have 18, right? 6, 12, 18, yeah. So we know we're adding 6, adding 6. So recursive is going to be function of n minus 1 plus 6. Our explicit will be the function of n equals 6 times n, and we'll leave it like that because on day 0, there's nothing, right? We're starting at day 1. And so for our graph, we have 1, 2, and 3 is at 6, 12, and 18. And so you would graph it like so, graph it like so, and we can spread it out. We can say that's 1, 2, 3, 1, 2, 3, and we can count it by 3s and call this 3, 6, 9, what am I doing? 1, 2, 3, 12, and then 16, 18 up there. All right, something along those lines. So 3, 6, and 12. So 12, something up here. 3, 6, 9, 12, and 18 up there. Something along those lines there. All right, so that's really it. Putting all together nice and simply. Hope that makes sense for you today. And again, just here to help you out. Hope it's working for you, and we will see you next time.